Alrighty. That was an exciting little hiccup there. Excellent. I see we've got 2 people for the start of things. So since there's anybody here, we might as well go ahead and get started. Hopefully folks will trickle in. I don't have the best view of who is here or not. Oh, okay. Excellent. I can do it on this screen. All right. So, I hope everybody is staying safe and healthy at home. This is going to be a little bit weird to get used to, but we'll figure things out as we go along. So, I'm going to start off by putting sort of a summary up here, just so that we have all the tools that we'll need to be using. Yell out in chat if you have a question. There'll be a couple of times that I have questions for y'all, and it's going to be a lot harder to wait when I'm sitting here staring at a blank screen, but I'll try to give us some time, especially considering that chat is on a little bit of a delay, just because that's how latency works. But today we're talking about section 4.1, which, as we saw from our reading summaries, is all about linear approximation. So the basic idea that we got in the book there is, whoops, that's exciting. I get to see the fan art that I do in my spare time. Alrighty, so back to this. Alright, so hopefully this won't crash too many more times. As I was saying, it rewrites our definition of the derivative using this concept of delta f and delta x. But it's just the same definition of the derivative we've been using. And if we remember what this notation means, what this guy means here, is that the closer delta, let me get that eraser out there, make that a little bit bigger. The closer delta x is to 0, the closer f prime of a is equal to delta f over delta x. So, as long as we're presuming that delta x is decently small, that's how we get the statement that delta f is close, not equal to, but kind of close, the derivative at that point that we're close to times delta x. And if we expand out what that delta f means, like we have in our book, then we get that just f of x itself is therefore kind of like this thing that the book calls L of x, which is the function at the easy to compute point. Oops. There we go. So again, both of these are if x is close to a, which is the same thing as delta x close to 0. And so partially the question might come up, why do we care, right? If we can figure out what f of a is, then surely we can plug in for x instead. But the idea here is that sometimes it's easier to plug some numbers in than others, right? If we have, say, a polynomial and we want to plug 1 in, well, that's really easy. We just basically get rid of all the x's and keep the coefficients. But if we want to plug 1.1 in, then we actually have to do some work there. So the idea is to avoid, or to only have to plug in numbers that are easy to calculate. So that's basically, well, there's one other thing that was introduced in this section, and that was the concept of error. That's not something special to this topic, or specific rather. They just sort of introduce it here. In general, error is always going to be the difference between your guess and what's actually true. So our estimation minus the real deal. And we put those absolute value bars there so that it doesn't matter what order we do that in, right? We always want our error to be a positive number. So again, that's not specific to linear approximations. That's just the definition of what error is. Alrighty. So before we go any further, and I possibly should have opened with this, considering that's what we usually open with. Did anybody have any questions they want to throw in chat for how things are going to go, things that happen from this section, things that are up on Canvas at the moment, anything along those lines? Alright, there is so much words I want this thing. So I'm going to keep going, and if you ever go back, if you have a question, no, I'm going to give another second to fill that out. Alright, I didn't figure out how to connect again. No. Okay. This right here, no, is not going to be on the take-home. The take-home is going to be based on stuff that we've covered so far. The take-home is going to be going up as soon as we close down the stream today. It was written last weekend, so it's not going to cover anything from today. It's going to stop at 3.9, 10? I don't remember which was the last one in Chapter 3. But it's going to stop with Chapter 3. Let's put it there. Okay, so my sound appears to be fixed. The take-home will be due a week after it's put up. So it's going to go up today. It's going to be due next Monday. I'm going to set the due date on the assignment to be 11:59 p.m. so you can turn it in anytime Monday. What you'll want to do is if you have a scanner or a digital camera of some type, if you'll take a picture of it. One thing that I would greatly appreciate is if you make sure that the picture is oriented so that up is up. I can do some things around it to fix that if it's an owner's burden, but it would be greatly appreciated if up was up on the picture. Also, you need to make sure that your picture is legible, which can be difficult to do when writing in pencil on paper. But that's sort of, I gotta be able to read it to grade it, so there's that. Alrighty. Well, if there are any other questions as we go through, feel free to throw them out there. But let's get doing some practice problems. So our first practice problem, we're going to estimate delta f for a particular function, which is the natural log of 2x squared plus 3x minus 1 at a equals 2 and delta x equals 0.15. That is hard to read on this screen. I'll make it a little bit bigger for us. There we go. So if we look at this, right, we have a formula right up here. That tells us that if we're looking for delta f, it's really close to that formula there. So we pick that up. And so estimating means that those wiggly equal signs is okay. So that's pretty much the definition of the wiggly equal sign, is that we're estimating it, not finding something that's equal. So that means that we need to figure out this stuff over here. Right? Now, part of this is already given to us as part of the problem. We know what delta x is. So really the key work of these type of problems is going to be finding that derivative. So I'm going to again try for this whole dead air thing and hope that it doesn't do weird things to my connection. But how do we take the derivative of something like this f of x? I know it's going to be hard to type over chat, but you can give basic ideas. You can tell me what rules we might use, and I'll extrapolate a little bit more than I might if you were able to say something out loud. Yeah, chain rule, right? So we've got an outside function here. We've got this natural log. Whoops, that's not what I want to click. So we've got our outside function here, and we've also got an inside function. We've got something that's being plugged into that natural log, right? And it's actually a little bit nicer than just the regular old chain rule, right? Specifically when natural log is the outside function. I mean, it's technically just the chain rule, and the chain rule is the main thing to remember there. But when natural log is the outside function, we can use the chain rule by taking the derivative of the inside. Right, so that's this guy up here. over the inside itself. Right? Because if we remember, the derivative of natural log is 1 over x. So the derivative of the outside, that natural log, with the inside plugged in, gets us this piece. Right? And then multiplied by the derivative of the inside is what gets us this piece. Right? And I'm not going to do the dead air for taking the derivative of a polynomial. Though, of course, if there are any questions, then we can throw them out there. So the derivative you get for this is, there's my connection again. So let me check. Is that what I got before? Okay, and my connection's good again. Alright, so we did the derivative to plug it back into that formula, but that formula specifically wants us to plug in f of a, and I realized I skipped a step here because we have from above that a equals 2. Right? So if we want to plug back into that formula, we need to plug 2 into that derivative we found, and then plug some stuff in. I'm going to zoom our canvas up a little bit, get some more whiteboard space. So that means delta f is approximately equal to f prime of a, which we discovered was 11/13, and delta x, which is 0.15. So if we want to simplify this, right, we could throw this into our calculator and it's probably going to give us some sort of longer decimal, but we can also just change that 0.15 to a fraction, right? That sort of thing is going to be useful because we're going to be mixing up a lot of decimals and fractions for problems in this section. So, easiest way is just to change the decimal into a fraction and then multiply your two pieces together. So I'm going to give it a little bit more dead air here to see if anybody has any questions about any of the steps that we worked through here. Alrighty, So again, you can always ask questions later. We can just scroll back up. But we'll move on to the next one for now. So in this one, we're going to do another estimate. We're going to estimate delta y for the equation y equals cotangent of the square root of x. And we're going to do it for a equals pi squared over 16. And delta x equals 0.01. Right. So, what do we need to do first? Yeah, so we need to take a derivative. Yeah, there we go. So we have our formula from before that delta y equals the derivative of y with a plugged in times delta x. So the first thing we need to do is take the derivative of y. Right? So how are we going to do that? Right, so that's another chain rule, right? We're plugging the something into another function. So what is our inside function? Right, exactly. That inside function is going to be the thing that we're plugging into cotangent x. Right? And so I'm going to go ahead and fill in the outside because it's the only thing left over. Right, so what is the derivative of the inside? And again, if it's hard to type, you can tell me what rule we're going to use or some things about it. There we go. Right, so this is a power rule, as we've noticed there, right? We're bringing that 1/2 power because that's what a square root secretly means, and we're multiplying it on the outside. And then we're subtracting 1 from it to get x to the negative 1 as the power. And just because I know it'll be useful later, we have this guy. So what about this derivative? Alrighty. Looks good to me. Right, so the derivative of cotangent that we have from one of our multitude of trigonometric derivative tables is going to be negative cosecant squared x. Right. So when we want to put all this together, right, the chain rule says to take the derivative of the outside and plug the inside back in. Alright, so if we remember, we sort of connect these guys. Right, and then we multiply it by the derivative of the inside. Right. So that's what we get for our derivative. So what's the next step to estimate delta y, to actually answer the question at hand? What do we need to do now? Right, so we need to plug a in, right? So we found the derivative, but in our formula, it's the derivative with a plugged in. So, and in this case, a is one of the things given to us. Right. So this is going to be negative cosecant squared of the square root pi squared over 16 times 1 over 2 times the square root of pi squared over 16. Now, cleverly, I chose an a that works nicely with a square root. All right, so this is going to simplify to pi over 4 in both cases. Right. And so not only does it simplify nicely under the square root, so we can get rid of the square root, but remember, pi over 4 is one of those numbers that we should know how to find all of the trig functions for. Right, so first off, right, we remember that that square there really means to plug in and then take the square of whatever's left. Right, that 2 times pi over 4 becomes pi over 2. I think we've reached the point where I can start using this space over here. Cosecant of pi over 4 is, if I did my work ahead of time right, because I don't remember that off the top of my head. That's what having notes is for. And if I want to simplify this complex fraction, which I do, because we always do, this is actually one of the nicer types of complex fractions to simplify when we have a single term in the numerator. Right? Because if we have a single term in the, single term in the denominator. When we have a single term in the denominator, we can just flip it upside down and turn it into multiplication. So pi over 2 flips to 2 over pi, times 1 gets us 2 over pi again. So we get negative 4 over pi. So the change in y is that it's going to go down for a little bit less than 1. So do we have any questions about anything we did for this problem? Yeah. So, this guy right here, that's not a great color to see on screen. Let's make it purple. I like purple better anyway. This guy right here, I know, is root 2, because pi over 4 is one of those values that we just know how to plug into all of our trig functions, and we know that when we plug it into cosecant, we get root 2. So that is something that you can either memorize, or if you're like me, look it up, have a cheat sheet for the final exam, though ignore that I said that. You just get to have your book and your notes on the final exam. So if I were doing it, I would look it up in my notes or my book. But that value is just one of the ones we should know. Right? And so when we have, anytime we have A divided by B over C, right? Anytime we have a fraction of that, the way fractions work is that if we're dividing by a fraction, that's the same thing as multiplying by its reciprocal. So that's the same thing as taking the numerator and multiplying by the reciprocal of the fraction. In this case, the A in question was 1, so we really just get C over B, and this here that we circle goes directly to this guy. Does that make it a little clearer? All right, excellent. There we go. Only 2 fingers at a time. Okay, note to self, I'm going to need to make these canvases much bigger, and my program's not going to like it. So, let's do one where we're not handed quite as much information, and see how we can get it. Alrighty, so we have here that we want to estimate the difference between two things. And the trick with identifying these is, at least so far, we've only talked about so many different estimation methods. Right? So if we're asked to estimate something, so that's the first clue. Right? And that something is a subtraction. That's the second clue. And if the two things that we're subtracting look very similar, that's the third clue. Right? So if we want to know when we're going to be using this linear approximation, at least if it's going to be a delta F type thing, then we're going to, first, it's an estimation problem. Second, it's a subtraction. And third, we're subtracting something that looks like it might be the same function with two different things plugged in. Right? So for all of our problems before, both of them, rather, we were given three things. We were given f of x, we were given a, and we were given delta x. Right? And anytime we want to do one of these problems, we need those three things, right? Our formula is that delta f, which I'm going to remind us real quick is f of a plus delta x minus f of a, or vice versa. These are allowed to be swapped. Is equal to f prime of a times delta x. Right? So in order to be able to fill this in, then we need to know what the function is so we can take its derivative. We need to know what a is so that we can plug it into the derivative. And we need to know what delta x is so we can multiply the derivative at a by it. So what do we think the function is in this problem? So to lay it out a little differently, right, if it's this type of estimation problem, then what we're trying to say is that this is delta f. Right, because that's the sort of thing that we estimate. This should be wiggly lines if I'm not trying to be bad. Right, so in other words, we want to match up sine of 91 degrees minus sine of 90 degrees with f of a plus delta x minus f of a. Right? So does that help us figure out what f might need to be for this problem? All right. Sounds good to me. Right. The other thing to think about is I sort of indicated it up here, right? The three things that tell us that this is a linear approximation problem is it says estimate, it's got a subtraction, and it's subtracting two things that look very similar, right? So the things that look similar in the two things that it's subtracting also helps us find that f of x. Right? So we talked a little bit earlier about a, right? Remember, a is the one that's supposed to be easy to plug in. So what's something that shows up in this problem that's easy to plug in for sine? What's something, so we're plugging two things into sine. Which one of them is easy to figure out what sine is at? So what of the two things that we're plugging in is it easy to calculate? 90 degrees, yeah. Right, so we're plugging in 90 and 91 degrees. 90 degrees is definitely the easier one to figure out what sine is. Right? So if that's what A is, right, you always need to figure out A first. Then what is delta x going to be? A is always going to be the one that is easy to plug in. Right? Sine of 91 degrees, I don't know what that is off the top of my head. Sine of 90 degrees, that's 0. At the very least, it's one of the ones that we should know off the top of our heads. Nah, it's 1. It's definitely 1. I was getting it mixed up with cosine. Right, so A is always going to be the one that it is easiest to plug into F. So if we're thinking about matching these two equations up, right, and we've already said that f of x is sine of x and a is 90 degrees, then f of a is clearly matching up with sine of 90 degrees, right? That's what the two things that we've already found are. Which means that these two, sine of 91 degrees and f of a plus delta x, should also be matched up. So, since we already know that F is sine, so those are matched up, that tells us that 91 degrees equals A plus delta X. So, what should delta X be? Right, 1 degree, exactly. Right. So there's another aspect of this problem that makes it sort of a trick question, but only in that I wanted an opportunity to remind folks about it, or tell folks for the first time, because we need to get at it. And real quick, so we have that 91 degrees equals A plus delta X. Right, so delta X by itself can't be the full 91 degrees. Right, if we plug in the A that we already know, then that's how we get that 1 degree equals delta X. Right. But one of the things that one of the words that I've been saying a whole lot here is one that we need to be careful about when we're doing calculus, which is the word degree. So in general, it's not necessarily super pertinent in this particular problem, but we need to be careful about using degrees when we're going to do calculus on trig equations. Namely, certain rules don't work quite as well if we're plugging in degrees. But we want to make sure that we remember how to switch from degrees to radians. It's sort of standard practice to go ahead and do that switch and to work in calculus with radians. It's something you'll generally be expected to do as you go through with this. All right, so does anybody remember what 90 degrees is in radians? All right, reminder, radians is going to be the ones with pi in it all the time. Yeah. So 90 degrees is going to be pi over 2. And does anybody remember the conversion factor? If you're having to change a not one of the obvious angles. So one of the things when you're converting two different measurements, I'm going to see if anybody has a question while we're waiting for this to die down. So, there we go. The trick for converting measurements is to get the two different units something that's the same measure, and make sure the one you're wanting to get rid of is on the bottom and the one you're wanting to keep is on the top. So there's any number of ways you can remember it, but sort of the easiest one maybe is that one revolution of the circle, right? One full circle around is 2 pi if we're measuring in radians, right? That's going all the way around a circle. And it's 360 degrees if you're measuring in degrees, right? So both of those are all the way around a circle, so when we multiply by 2 pi radians over 360 degrees, then we are really just multiplying by 1, because those are the same measurement, right? The degrees are going to cancel each other out, and we just end up with pi over 180. Right, so 1 degree is pi over 180 radians. So now we have what we started with on all of the other problems. We have our f of x, we have our a, we have our delta x. So what do we need to do first, now that we have all of this stuff? Now that we've analyzed the problem, we need to actually start working the problem. Yeah. Now we need to find the derivative and we need to plug a into it. Right? So what's the derivative of f? Cosine of x, exactly. So the derivative of sine is cosine. So what happens when we plug pi over 2 into cosine? 0. Exactly. Alright, so we plug it in there. So we get that as far as we can estimate using this method, there's no difference between sine of 91 degrees and sine of 90 degrees. Right? They are very, very, very close together. Right? So I'm going to expand our canvas a little, if it'll let me. I've already made it big enough that it is unhappy with me. Oh, okay. So let's not do that. Instead, we'll make a brand new canvas. Okay. So were there any questions over anything we did? I realize I probably should have kept it up here for questions. So I'll go back to it real quick. So are there any questions about... Yeah, absolutely. Sorry about that. Any questions about what we got here? I will play around with ways if I can figure out some way to get us more space on one page, because that would be ideal. But so that was this one or this one? So 1 or 2? Okay. So for that one, I was using the formula that this was delta F, remember, and this is approximately F prime of A, which we figured out above was 0, times delta X, which we figured out here in 1 was pi over 180. Yeah. Any other questions about stuff we got here? Alrighty. Okay. So, we've got our canvas set up. So, now we've got a word problem. Yay! Okay, so we have that the volume in liters and the pressure in atmosphere of a certain gas satisfy this equation P times V equals 42. We've managed to measure the volume, and our measurement equipment says that it's 6, but it could be as little as 5.75 or as much as 6.25. Right, so our measurement equipment is not the most precise. There's a little bit of error possible there in our measurement of the volume. Right? So one thing about word problems like this, right, is that when it says compute P, it means based on our measurement, what should P be? Far too many letters rhyme with each other. And then once we've done that, right, one thing we need to be careful, right, error came up in a very specific context in this case, but its general definition, the one that we talked about at the beginning of this session, is that error is the difference between your estimate, what you guess, and what is actually true. Right? So, in this case, the error that we're talking about is the difference between our guess, which is P when V equals 6, minus the actual P. And so what sort of information do we have about when this error would be at its maximum? Like, what would have to be the case for this to give us the maximum error that we could possibly be computing? So one thing to think about is that this P came from when V was a specific thing, right? We're presuming that V is 6, and we're computing what P is, right? So what could V possibly be that would mean that this computation right here is the most wrong? What possible values could V take so that that computation is the most wrong? Yeah, right? So this would be when and there's another option there, right? but we'll talk about as we go on how those actually get us the same number. So let's see. Okay, voice is back to good. So this is clearly, as we talked about before, gonna be a problem solved using linear approximation, not just because I wrote it in this section, right? But it is a well, this should probably say estimate to make it a really good thing. But it's a subtraction, right? That was one of our things here. And it's the same function, just with two different values plugged in. Right? So, let's get ourselves a little bit extra room. Let's do this easy piece first. Right? So, if v equals 6, what's p going to be? Right, 7. We know that p times v has to be 42. So if v is 6, p has to be 7. Right? And to get the other piece, we're going to need to come up with p as a function of v. We're going to need to come up with an a. And we're going to need to come up with a delta x, just like we did in the last problem. Right? Because we determined that this was a linear approximation problem to figure out what delta p is. And anytime we want to estimate the difference between two things that are different values being plugged into the same function, then we need to know the function, the a, and really this should be delta v. So where did we get, there we go. Thank you. Yes. Alrighty. So, we've got our computing v. We want to find our max error here. So, what is p as a function of v? Putting some notes in for people to follow along with later who don't have the benefit of helpful chat. So we have here an equation that has two variables in it. And anytime we have something like that, we can make one a function of the other. Right? So all that really means is making sure that one side is just P, and that's the only P that shows up, and the other side is allowed to have V's wherever it wants. So what do we get when we solve for P here? Yeah. Right, so if we want to solve this guy up here for P, that just means moving the V to the other side, and we do that by dividing both sides by V. Right, of course this means that V is not allowed to be 0, right, but we've already said that V is either 6 or within 0.25 of 6, and so 0 is not included in that range, right, so it's fine to divide by V. Right? Okay, so we have our P as a function of V, and we know that the two things that we want to plug in are 6 and 6.25. So which one of those should be A? Which one of those is it easiest to compute P? Yeah, there we go. Right, it is at least hopefully easiest because it's the one we've already computed. Usually when you've already done something, that's the easiest thing to do. Right. So, we've got our P. We didn't. Later we're going to say that, or I'm going to show you why those are the same. Okay, looks like I should be able to talk again. Okay, excellent. So, I mentioned earlier that we have these two options, right? Either V is all the way up at 6.25 or V is all the way down at 5.75, and I claimed that that's not going to change the problem, right? And it's because of what happens right here. So if we're saying that we're going to go with v equals 6.25, what's our delta v going to be? How do we get from 6 to 6.25? Right, so 6.25 minus 6 is 0.25, right? So that's our delta V if we have, if the V that we're going with is 6.25. What about if the V we're going with is 5.75? Oh, careful. That's not how we get from 6 to 5.75. Right? We're starting at 6 and we want to get to 5.75. What do we need to do? Right? We don't need to go up by 0.25. If we go up by 0.25, not quite. You're a little bit closer last time. Though I guess that could be seen as answering my secondary question, not the first one. Right? To get from 6 to 5.75, we need to go down by 0.25. Right? Whereas getting to 6.25, we go up by 2.5. Getting to 5.75, we go down by 5.75. Right? So the other way to write that would be saying that. Right? You always want to put your other one minus your A to actually calculate what your delta is going to be. Right? So we notice that those are the same number, just one with a negative and one with a positive. Right? So the other thing we might notice are these absolute value bars that we drew. Right? So our final answer here, our delta, absolute value of delta P, is going to be the absolute value of P prime A times delta V, right? And it doesn't matter whether that's negative or positive, the absolute value is going to make this be the same. So the absolute value of P prime A times 0.25 is equal to the absolute value of P prime A times negative 0.25. Right, so this isn't some sort of universal rule that you never have to worry about whether it's positive or negative, but in a case like this, where you're using this approximation to calculate an error, then you don't really care whether you went up or down, because that negative is going to get absolute valued out. Right. We are a little bit over time, and I don't want to steal anybody's time more than I said I would, so I'm going to go through this next little bit without pausing for questions, just so that we have this problem completed. Right? The next thing would be to get P prime of V, right? So take the derivative of P with respect to V. This is secretly 42 times V to the negative 1, right? So we can use the power rule on it and get 42 V to the negative 2, right? Which is negative 42 over V squared. So P prime of A going to be negative 42 over 36, which I simplified at some other point in my life as negative 7 over 6. So the absolute value of the difference in P, which is going to be our error, is, again, this should be approximate, going to be the absolute value of negative 7/6 times 0.25, which, like we did in that very first problem, I'm going to translate that to a fraction, because that works better in my mind. Then I'm going to multiply those together, get rid of the negative because we're an absolute value, and get the E maximum error is that guy there. Any questions? Alrighty. So, as a reminder, the VODs stick around here for 2 weeks. You can click the videos thing that shows up above this screen here where I'm writing to get at old videos. I'm also going to be uploading them to YouTube. I don't know how long that'll take with this more significant video file that I'm about to put up. And I'm going to put up the final screens and the time lapses up on Canvas. So you'll have these to refer back to later. I'm sorry about the sound issues. It's clearly not actually the closed captioning that's causing the problem. Oh, yes, thank you for reminding me. If y'all want to follow, that will mean that you get a notification whenever this stream comes online. So if it'll help you to remind you to show up in a given day, then that might be good. As a reminder, the stream will also pop up if someone has a question during office hours. So if you get a notification and it's at a weird time, then that's probably just because somebody had a question during office hours and we wanted to do something on the whiteboard. Right? So thanks everybody for showing up and participating. I really appreciate it. It worked out a bit better than I expected. Sound issues aside. So as usual, let me know if you have any questions about any of the ways this is going to go. Office hours are the usual times that are in the syllabus. You can contact me on GChat or via email. I'll be checking both of those regularly. And I'll see y'all Wednesday, hopefully. Stay safe and stay healthy.